So in this video, we are going to be looking at section 2.2, and we're going to be looking at the first part. And the first part that we're going to do is just going to begin to analyze characteristics of polynomial functions, specifically applying the leading term test. Also, this lovely image right here is probably one of my favorite images. This is Texas. This ain't Texas, so you know, Texas is the best. So before we get started looking at more complicated polynomial functions, let's first look at monomial functions. And we can actually look at this function right here, f of x equals x minus 2 to the 5th power, and know exactly how to graph it without even using our calculator. We can remember what we learned about transformations in chapter 1 and see that the x to the 5th function is actually shifting to the right 2 units. Remember, we take the opposite. And so our x to the 5th function, our parent function, is actually going to behave very similarly to our x cubed function, which, if you'll recall, goes to the origin like this. The only difference with this function is that it's going to flatten out a little bit more here, and it's also shifting to the right 2 units. So we can graph that by having it look something like this. So it's flat, more flat, and it's crossing at x equals 2. So that is the first type of monomial function. The second that we can look at is one that is going to behave similarly to the x squared function. So if you remember that, that is a parabola that if it's positive, it's going to be facing upward. If it's negative, it's going to be facing downward. So we see that our exponent here is even, but that we also have a negative constant term in the front. So we know that our graph is going to look something like this. It's going to be flatter here on the bottom of our function here, and it's going to be facing downwards. But we also see that our function is being shifted up 1 unit on the y-axis. So that is going to create this function right here that is shifted up. So if we apply that to our graph here, we're going to get something like this. So it's a bit wider, it's a bit flatter up here than your normal parabola. But these are just 2 examples of transformations of monomial functions, and we'll apply their similar techniques when we're examining polynomial functions. When we are given a polynomial function, we are going to look at it in a couple of different ways. And I just want to stress right from the beginning that we are going to graph these polynomials without using our calculator. So we are going to learn all different types of techniques in order to determine the different characteristics of the polynomial, where it is shifting, where it is turning, where it's increasing, decreasing, what the end behavior is doing. And we can do that all algebraically and determine what is happening. So first, right here, you see that this is kind of a crazy looking equation, and it may not make any sense, but let's try to break it down. So this is called the general form, and this is the general form of the polynomial function. So this a sub n term right here, this a sub n minus 1, this a sub 1, and this a sub 0 term are all considered constants. So they would be like numbers such as 2, 3, 1/2, -2, any numbers that are constant like that. This n right here is the exponent, and these are going to be in decreasing order. So if this is an x cubed function, this one is going to be an x squared function. Right? And then we can continue down until this is going to be the x to the 1st, and then this term is just going to be our constant, so we have no x value here. So this is the general form of our equation. All polynomials are going to take this form. And now we're going to determine what, given an equation, what the end behavior of the function is going to look like. So in the general sense, we are going to look at all the different possibilities. So the first one we're going to look at is what is happening to the end behavior. What is happening to our graph when our n is odd? Meaning when our exponent right here, when this is odd. So when it's 1, 3, 5, 7, anything like that. And then also what is happening when our a sub n term, this first term right here, is positive. So we want a positive a sub n term, an odd n term. So let's think of that in terms of numbers. Let's say we had 2 times x to the 3rd. So let's say that was our first term. So what we're going to do is we are going to see that when our n is odd and when our a sub n is positive, our graph actually is going to have an endpoint that is coming up this way and an endpoint that is going this way. We have no idea what is happening here in the rest of the function, but we do know our endpoints are going to be, the right side is going to be going up into infinity, and the left side is going to be going down into negative infinity. So when we look at the limit, we would say that the right endpoint is going to infinity, and the left endpoint is going to negative infinity. Similarly, we can look at the case when n is odd again, but this time a sub n is negative. So here, n, our exponent is going to be odd, but our a sub n term is going to be negative. So using the same numbers, we could give an example of if our first term is negative 2 times x cubed. That's the first term of our polynomial. We know automatically what the end behavior is going to do. So what this one is going to do is it is going to, instead of going up to the right, it is going to go up in the left, and then it's going to end down like this. So if you remember with our odd functions, just think back to the x cubed, right? So our function is like this, and our endpoints are going in opposite directions. So same thing here. Even if we have some crazy polynomial where our first term is 2x to the 107, because 107 is odd, we know exactly what our endpoints are going to do. So this time when we look at the limit as x goes to infinity, our f of x is going to be negative infinity. And as x goes to negative infinity, our y values are going up into positive infinity. So we write it just like that. So these are two examples when our n degree, so we have an odd degree polynomial, when a sub n is positive and when a sub n is negative. Now we're going to look at what happens when our n, our exponent on our first term, is even. So the first one we're going to look at is when n is even and a sub n is positive. So again, if we decided, if we want to use numbers, we could say 3 times x to the 4th. So if this is the first term of our polynomial, our function is going to look something like this, where our endpoints are going up into positive infinity on both sides. And we can relate this to the graph of a parabola, right? When we have f of x equals x squared, our graph looks something like this, where both endpoints are going up into infinity. So here, when our a sub n is positive and our n term is even, both of our endpoints are going to be going to positive infinity. So the limit as x approaches infinity and negative infinity is both going to be positive infinity. Finally, when we have our n term is even, so we have an even degree polynomial, but our first term is negative. So if we had negative 3 times x to the 4th, we would now have our endpoints that looks something like this. So our end behavior of our graph would both be going down to negative infinity on both sides. So we'd write that like this, where the limit as x goes to positive and negative infinity of f of x is negative infinity. Again, we have no idea what's happening in here. We could have some crazy long polynomial, but for now we're just using the leading term test in order to determine what our endpoints are doing. What is the behavior? All right, so let's look at an example. We have this function, g of x equals 4x to the 5th minus 8x cubed plus 20. Now, if we are applying the leading term test, the only thing we need to worry about is this term right here. So we see that our a sub n term is going to be positive 4, so it's positive, and our n term is odd. So automatically we can determine, using the rules that we just talked about, what the end behavior of our function is going to look like. So since it's odd, our function is going to be going in opposite directions. Our endpoints are going to be going opposite, and since it's positive, we know that it's going to be in this quadrant where it's going to infinity, and this quadrant where it's going to negative infinity. So our graph could be doing something crazy up here, but we don't know this part of the graph, so we can't even assume. All we know for sure are what the endpoints are doing. So we could write this in limit notation, saying the limit as x goes to infinity of our function g of x equals positive infinity, and the limit as x goes to negative infinity of our function g of x equals negative infinity. Again, this is exactly what we just talked about. Now, one more example before the end of the video. Let's again apply the leading term test in order to determine the end behavior of this function. So this polynomial function, we see our a sub n term is negative, and our n, our degree of our polynomial is even, So here, we don't have to know what's happening to the rest of the function yet. All we need to know is what the endpoints are doing. So because it is even, both of our endpoints are going to be going up or down in the same direction. So they're both going to be going up or they're both going to be going down. This term right here is going to determine whether they're going up or down. And because it is negative, we know that both endpoints are going to be going down. So our graph is going to have endpoints that look like that. We have no idea what's happening up here in this function, but the leading term test is only concerned with what is happening at the endpoints. Finally, we can use limit notation in order to describe this. So we would say the limit as x approaches infinity of our function g of x is equal to negative infinity, because as I'm going to positive infinity on my x, my y values are going to negative infinity. Similarly, as x goes to negative infinity, my y values are also going to negative infinity. So that's how you would denote the end behavior using limit notation.